Illinois. So Bharat has quite a background. He's interested in everything. So he started out in his PhD at Stanford, where he studied cosmology and made some important contributions during the early days of inflation. And then he moved to string theory, did that for a while, made some important contributions there, then moved back to cosmology and did this to brush up on his cosmology, went to Princeton and worked with Jim Peebles. And there invented dark energy. That's what we call it now. It was 10 years before there were observations of the accelerating universe, which is a pretty good trick. So he's remained interested in many things, but particularly cosmology, and he's always on the lookout for new tools. So his recent work has touched on all kinds of astrophysics that he uses for cosmology, obviously the CMB, but also I think we'll hear about AGN and gamma ray bursts. So for a long time, he's been a distinguished professor at Kansas State in Manhattan, Kansas, the Little Apple. He's won numerous awards, and just to mention a few, there's not time for all of them, but he's a fellow of both the American Physical Society and the American Astronomical Society. And most recently, he won the very prestigious APS Lilienfeld Prize, which recognizes you have to be like doubly excellent for it because it recognizes excellence in research, but also in public engagement. And he's not only lectures wide and far, but he also runs this outreach project for teachers and students in the Midwest. So with no further ado, take it away, Bharat.
Thank you very much. That's a very, very generous introduction. Thank you. So before I start, I just want to point out this website. It's got some really nice and simple, clear videos of global warming, and it's kind of probably a useful thing to publicize. So I'm a cosmologist, and it's a really nice time to be a cosmologist because of all the data that's coming in. And these data are reinforcing two very striking results. So the first one is that we don't understand 95% of the constituents of the current energy budget, the cosmological energy budget. So we understand at some level the 5%, which are the atoms and molecules and charged particles. And that's really, really interesting because 95% of the stuff out there is waiting to be understood. And the other result that's getting reinforced, that's even more profound if it holds up, is that either quantum mechanics or relativity or both are incomplete descriptions of reality. And if that gets reinforced by more and better data, that's going to be very revolutionary because quantum mechanics and relativity are the foundations of physics, and they've been that way for over a century now. So let me start with this really quick summary about the energy budget of the universe at the present time. So we know that about 5% of it is baryonic matter, and that's mostly atoms and gas clouds and stars and elephants and blue whales and humans and a lot of other stuff. And this number started getting pinned down in the 1960s through the work of Gamow and his postdoc Alpher and his student Alpher and his postdoc Herman. And they were trying to explain the abundances of the light elements, and they realized that there'd be photons left over. And through a very inspired guess, they predicted those photons would be in the microwave part of the spectrum. And those photons were discovered about 20-something years later at Bell Labs by Penzias and Wilson, who didn't quite understand what they discovered, but they'd done a really, really great experiment, and the explanation was followed in a companion paper by Dickey Peebles, Roland Wilkinson. Even before that, in the 1930s, Zwicky was looking at clusters of galaxies and studying how fast they were rotating around each other. And he said if these motions are caused by gravitational forces, then he can determine the masses needed to produce those gravitational forces. And he realized that he needed much more mass to produce the motions than was possible through the masses he could measure in stars and hot gas. So he discovered dark matter, and the motions he was measuring were hundreds to thousands of kilometers a second, which is non-relativistic or cold. He didn't know this number, so he couldn't say anything about it being non-baryonic. That came later after this number got pinned down. But that happened in the 70s through the work of Vera Rubin and her collaborators and other people. Um, and this number started getting pinned down then. And more recently, people have discovered something even stranger, and they've named it energy to distinguish it from matter. And this is not energy in the sense of kinetic energy or mechanical energy or anything like that. It's just a different name for the substance to distinguish it from matter. It's also dark. It doesn't absorb or emit light. And if it's made up of particles, these particles have masses of order 10 to the minus 33 eV. And those are very, very light, and they're going to be traveling at very high speeds, close to the speed of light. So this is relativistic motion. And it's also non-baryonic, and this is the biggest contributor to the energy budget now. And this was discovered by the supernovae observations in the late 1990s. So we basically don't understand 95% of the current energy budget. We don't know anything about these guys other than that they have some gravitational fields, and that's all we can see because they make the light move around, the shiny stuff move around. But we do have a standard model of cosmology. So what I want to do is I want to motivate dark energy, and then I'm going to look at a couple of illustrative models. So there's the standard model with the cosmological constant and cold dark matter. And there's a model that turns that into a scalar field with the potential energy density. And there's a couple of parameterizations that are incomplete but are really widely used. So they model the dark energy as a fluid with an equation of state, and I'll come to those equations of state soon. And these are kind of arbitrary, and they have more free parameters than the models, but they're easier to work with. And so we're going to take these models and make predictions and compare their predictions to the observations and see how well those observations can be used to constrain the model parameters and test consistency between different data sets. And then I'll move on to discussing the transition from decelerated expansion in the earlier universe, where matter dominates, to the accelerated expansion now, where the dark energy dominates, and talk a little bit about the value of the Hubble constant, look at measuring spatial curvature, and then talk a little bit about an issue in the Planck PR3 data that seems to be suggesting that there's some excess weak lensing, and then the DESI results, and hopefully I'll get to this before the end of the talk. So we don't have great cosmological data. It's much, much better than it used to be, but it doesn't compare to particle physics data you can get at the CERN, LHC. And so you can't really make any model independent predictions for cosmology. And so what you can do is you can try to parameterize your model and your ignorance in half a dozen parameters and try to use those parameters and constrain them with the data instead of trying to make model independent predictions. And you can, if you use a bunch of models, you can see whether your conclusions are independent of the model. And I'll show you examples of that. And you can also use these models to get tighter constraints on these parameters because you're only trying to constrain a few parameters. And you can compare different data sets in the same model and see if they favor the same part of parameter space. And if they don't, then either your model is wrong or there's a systematic error that you've been neglecting in one of the data sets. And this will start making a lot more sense when I show you explicit examples. So everybody knows the Hubble law. That's the recession velocity is proportional to the distance, and the constant of proportionality is the Hubble constant. And my favorite value of this is about 68 plus or minus 2.8, and I'll try to motivate this in a second. So this law holds at all times, except the constant of proportionality depends on redshift. And when you're looking at it earlier times, that's called the Hubble parameter. And the Hubble constant is the current value of the Hubble parameter. And this is an example of the Hubble laws. This is a very famous plot. It's the final key project, HST key project result. That key project was led by Wendy Friedman. And you can see the recession velocity and the distances here. And this straight line was the best fit. And then it was 72. And this paper came out in 2001. And Rich Scott, Michael Vogley, and the graduate student of mine, Sophia Podariu, and I also tried to measure the Hubble constant in 2001, except we used a different technique. So Hukra had 270 odd measurements tabulated, and we took those and we saw that when you plotted up the histogram, they followed a completely non-Gaussian distribution. And so that tells you, if you believe that there's a single Hubble constant, that tells you that the error bars are underestimated. And so we threw away the error bars and we used median statistics. And we did that again in 2001, 2011 in this paper with 553 measurements. And that's how we got this. And this error bar includes the systematic errors also, the purely statistical part at ±1. And you can get the systematics because in these 553, we had about 10 different techniques that had enough measurements of the Hubble constant to get the median values for those distributions. And the scatter among the medians gives you the systematic error. And the Hubble constant, right now, there's about 800 measurements. It's the most measured parameter in science, as far as I can tell. And so this discrepancy has been around for a very, very long time. So some people have a higher value. It used to be 100, and some people had a lower value, and that used to be about 50. But more recently, it's kind of converged to maybe about 73. This is again from 10, 15 years ago. 74 then and 68. And what I'm showing you here is fitting the ΛCDM model to data from 7 years of WMAP and smaller scale anisotropy data and galaxy clustering data. And I've extended the ΛCDM model to allow for extra light neutrino species that's parameterized by this number and effective. And then we use these as Gaussian priors and do the analysis and marginalize over the other 5 parameters of the ΛCDM model. And these are the contours we get in this plane. And you can see that the blue ones are shifted more towards 3. So in the standard model of cosmology, a standard model of nucleus and of neutrinos, it's roughly, because the way things decouple, it's about 3.046 degrees of freedom. And the blue ones are completely consistent with that, better than 1 sigma. The red ones about 2 sigma away. So you can see that the standard model of particle physics, which predicts that many neutrino species, favors 68 over 74. And that's pretty remarkable because 15 years before this, we didn't know the Hubble constant to a factor of 2. So we have an expanding universe. There's privileged observers at rest with respect to the expansion. And those are the observers for which the cosmological principle holds that the distribution is statistically isotropic on large scales. And that implies spatial homogeneity. And then with taking the simplest global topology, you get the 3 standard Friedman-Lemaitre, Robertson-Walker models with the line element up here. These are the 2-dimensional analogs. I can't draw the 3-dimensional ones. So we have the flat, and that's going to go out to infinity in both dimensions, the open and the closed. And curvature is positive, 0, and negative. And the density parameter, this is underdense, overdense, and critically dense. And we need a equation of motion, and the dynamical variable is the scale factor. So if you take a simple model for the matter, it's just an ideal fluid with an equation of state, and rho is the energy density, and the Friedman equation, the time derivative of that squared, is governed by the mass of the energy density in the matter fluid, space curvature, and lambda. And you need to complement this by the energy conservation equation. So it's just PDV work. And that introduces pressure. So you need an equation of state. And these are the 3 equations you need to solve. So you know that H, which is A dot over A, is positive. Things are redshifted. And the next thing you might be interested in is what's happening to that Hubble parameter whether it's increasing or decreasing with time. Is the expansion speeding up or slowing down? And you can work through this with a little bit of calculus and get the acceleration equation. And that acceleration is being sourced by the matter part, that's the cold out matter, and the baryons. And if I hadn't used natural units, there'd be a c squared in the denominator. So this is the relativistic effect. And we can introduce the cosmological constant here. So space curvature doesn't show up in this equation. And so if we ignore this for a minute, we can see that because of this negative sign, that ordinary matter and cold dark matter prefers deceleration. And so if you go out there and measure and find A double dot is positive, you either have to discard GR, or you can say that you're going to take advantage of the fact that T mu nu on the right-hand side is somewhat arbitrary, and then you can introduce a cosmological constant and choose this equation of state for it. And then this stuff in the round parentheses becomes -2 rho lambda, and you choose rho lambda to be large and dominate over this, and the minus sign makes everything inside the square parentheses negative. And that negative sign cancels this, and you get this accelerated expansion. And that's why we introduced dark energy. So there's two useful comments about this. This would be a really stupid thing to do if you just had one measurement and you're trying to patch up GR. But you have about half a dozen different measurements that all suggest roughly the same amount of dark energy. So it might not be that stupid to introduce this. And the other thing is that in the lab, we see this effect in things like the Casimir effect and the Lamb shift, where you have modified vacuum states, that they're no longer a free field vacuum all the way to infinity. And those 0-point fluctuations behave like a cosmological constant. And the hope is that something to do with quantum mechanics can explain this. And this parameter omega I'd introduced before was just the ratio of whatever substance you are to the critical energy density. And that's in the Einstein de Sitter model where K is 0 and lambda is 0. Then the energy density is completely determined by the Hubble constant and Newton's constant. And the scale is roughly 10 to the minus 29 grams per cubic centimeter. So dark energy, this is a cartoon explanation of how dark energy is discovered. So if we look at the Hubble law in a slowly expanding universe and a rapidly expanding universe, a galaxy at the same distance in these two universes will be moving away faster in this one compared to this one. It has a bigger V. And as you go out to further and further distances, you're looking at things at earlier and earlier times. So there's three possibilities: that the expansion rate of the slope of the Hubble law is a constant, or in the past that it expanded more slowly, and as it came to the present, it sped up, or in the past that it expanded more rapidly, and as it came to the present, it slowed down. And in the 1990s, the things you could see the furthest out with and that you could use as standard candles were the type 1a supernovae. And they all ended up in the blue part of the diagram. And they favored this model, that the expansion was speeding up. And all of you have probably seen plots like this. This is a really old one of the density in the cosmological constant of the density parameter and the density parameter in cold dark matter and baryonic matter. And if there was no dark energy, you'd have to lie along this line here. But the supernovae forced us up here. And this was a little bit more, roughly a little bit less than a 3 sigma detection than 20 years ago. And now it's about 4.5 or 5 sigma detection of dark energy that's away from omega lambda equal to 0. So again, in this type of equation, it's telling you that B has to be less than minus rho over 3 overall. And that gives you the accelerated expansion. So we know that there's dark energy there, and we also know that it's a major contributor to the current energy budget. But there are other questions we can ask, like whether it's actually a cosmological constant or whether it varies in space and then it has to vary in time. And to answer these questions, you have to make some assumptions, and it's very important to remember these, that you're assuming that GR is correct, at least in the way I go about it by modifying T mu nu, and that the astronomers have pinned down their systematic errors well enough for you to believe their results. And the simplest way to look at stuff like this is to build models with dynamical dark energy and then test their predictions against observations. So I'll show you a bunch of plots like this. It's going to be a log-log energy density against scale factor. And this is at late times, so I don't care about radiation. And so this is the standard model, and this is the Friedman equation. You have dark matter and baryons. And from the energy conservation equation, you know that they go as like 1 over the volume, and that's 1 over a cubed, and that's the blue line. And space curvature is the orange line, it's 1 over a squared, and the cosmological constant is this horizontal line. So over here, dark matter dominates, and you get decelerated expansion. And by the time you come here, dark energy dominates. The green line's higher than the other two, and you get accelerated expansion. So it seems you have 3 parameters here, but we'll see in a second that there's a sum rule, and that this constraint has to be satisfied. So there's really only 2 free parameters, and conventionally, they're taken to be the matter density parameter of the current epoch and the lambda density parameter, which is independent of time. And you can see immediately from this what upsets particle physicists. So this green line is an energy per unit volume, and if you turn that to natural units, it's an energy to the 4th power. So if you take the 4th root of this, that tells you what the energy scale is of this phenomenon. And that energy scale is roughly 1/10 of a millielectron volt. And that's not something that people thought was fundamental in physics for a very long time. Things have changed a little bit, and I'll come back to that in a second. But it's the energy scale of chemistry, and it's pretty clear that chemistry is not fundamental to a particle physicist, and obviously that rules out a cosmological constant. But right now, so neutrino masses are coming in at this scale, and so people are trying to connect neutrino masses to dark energy, and I haven't seen a very convincing model. But there's a very easy way to deal with this problem. So all you have to do is tilt this line a tiny bit, and the universe is really, really old. So even if you give it a tiny slope, at really early times, it can correspond to a much, much higher energy density scale. And you can do that in a number of ways. So this is the WCDM or XCDM parameterization. And to make life simple, I'm going to first show you the spatially flat case. So you have the usual dark matter and baryonic matter. And then you have another fluid, which we're going to call the X fluid, that has an equation of state of this form. And if you choose W sub X to be less than minus 1/3, then you get this to give you accelerated expansion now. And so you have a sloping straight line over here. There's a problem with this. The moment you make W sub X negative, you take dp rho, and that gives you the speed of sound squared, and that gives you an imaginary speed of sound if W is negative. And that tells you, if you kind of just think of the Jeans instability, that you're going to have exponentially growing inhomogeneities, and it's not going to look at like our universe at all. And so the way people get around this is they just, for the perturbations, they assume the speed of sound is unity and do the computation that way, but this is not a consistent physical model. And the parameters we conventionally choose for this model are omega matter now and W sub X. And you can make this into a consistent model by making a scalar field do this. So I'm going to introduce a scalar field with a potential energy density. So there's a kinetic energy density. So this is the energy density of the scalar field. There's a kinetic energy. That's a dot. It's a phi dot squared. And I've chosen this potential energy as an inverse spiral on the scalar field. And that's going to contribute here. But no, this is a dynamical variable, so you have to write down the Klein-Gordon equation. That's two dots up there. That's a single dot, and this is the Hubble drag, and this is dv d5. And you have to numerically integrate this. So when you numerically integrate this, you find that it's got a slope that tends to get a little bit shallower as time goes on. And it doesn't just do this in the baryon dark matter dominated epoch. So if you saw this in the radiation epoch, it also does it there. So this potential is kind of special, this potential energy density. It has an attractor solution that wants to try to dominate whatever the dominant source of T mu nu is already in that epoch. And so this can explain this fine-tuning as to why, or the coincidence problem as to why the energy in the cosmological constant is roughly comparable to the energy density in matter now. But it makes life a little bit more difficult because you have to solve these equations numerically. And I'll quickly illustrate this with older data sets because the error bars are bigger and you can kind of see what happens. And these are just illustrative. I'll come back to the newest data in a few minutes. So we look at type 1a and baryon acoustic oscillations and Hubble parameter versus redshift and growth factor versus redshift. And the procedure is pretty straightforward. So instead of working with the scale factor, we work with redshift and rewrite the Friedmann equation in ΛCDM model in this form. And we can see at z equals 0, this becomes h naught squared. And so this becomes unity, this becomes unity. And so that's where that sum rule comes from. So there's only two free parameters here. And conventionally, we choose it to be these two. And then we can re-express this in terms of redshift, in terms of the cosmological parameters, in terms of the Hubble constant through this thing inside the square brackets, take the square root of that. That's the expansion rate, the normalized expansion rate. And so if you have measurements of this side, you make predictions for that at the same redshift, and then use whatever technique you want to constrain the parameters. And I'll show you some of these constraints. So I'll be showing you lots of plots like this with lambda CDM here, X CDM or W CDM here, and phi CDM here. So on this axis, it's going to be omega matter, omega matter, omega matter at the current effort. In the lambda CDM case, it's omega lambda. In the X CDM case, it's W sub X. And that's spatially flat. So at this value of W sub X equal to -1, it becomes a lambda CDM model, spatially flat. And this guy is alpha for the scalar field. At the spatially flat lambda CDM model is at alpha equals 0. And in this plot, the spatially flat lambda CDM model is along this dashed line. So the closed models are up here, and the open models are here. And up here, you have dynamical dark energy above and below. And this is quintessence-like when W is greater than -1, and it's phantom-like when it's below -1. And this is always quintessence-like, and it's dynamical all the way up here. So you can also see these dotted lines, and these tell you that in this part of parameter space, you're accelerating at the current epoch and you're decelerating down here. And the same thing's true here and here. And the solid lines are the constraints you get from this older type 1a supernovae data. And you get the 1 sigma, 2 sigma, 3 sigma, and that's the best fit. And 1 sigma, 2 sigma, 3 sigma, and best fit. And 1 sigma, 2 sigma, 3 sigma. So there's a whole bunch of things you can conclude from this. So independent of cosmological model, whatever model you use to analyze this data, most of the likelihood is in the accelerated part of parameter space. And they're consistent with the standard model of cosmology, which is omega matter about 0.3, omega lambda about 0.7, and spatially flat. And it doesn't matter whether you're looking at this case, again, 0.3, then because this is spatially flat, omega lambda is 0.7, and again, 0.3 is over here. And they're all consistent with that. And you can have some space curvature and you can have some dark energy dynamics. So this data are not good enough to give you really strong constraints on space curvature, dark energy dynamics. If you look at BAO, you see the same sort of thing. Most of the parameter space is the accelerated part, and the standard model is right close to the peak. And it doesn't matter what data set you use, but the most important thing is you can look at the way these contours are aligned and compare those alignments to the way these guys are aligned. And you can see that they're almost orthogonal, so you can anticipate that if you combine supernovae and BAO, you'll get much tighter constraints. And you can look at the Hubble parameter constraints, and because the Hubble constant is one of the Hubble parameter values, there's two values for it, and you shift things by about half sigma, but they're both consistent with the standard model. And the growth factor, you draw similar conclusions. So it's really, really good. Is that a question?
Yeah, on the previous slides or on the ∅CDM, it looks like the best fit is down at where the index is 0.
Right.
What does it do physically?
That corresponds to lambda CDM.
Oh, okay, so we're one.
Yeah, alpha equal to 0 is lambda CDM, so it behaves like a cosmological constant. So this is the really, really important point, that the constraints from these different data sets are not inconsistent. So maybe you're doing something sensible. More precisely, you're constraining omega matter to be about, omega lambda to be about 0.7 and omega matter to be about 0.3 and to be spatially flat. So it's consistent with the standard model. So then you can do the obvious thing, do two data sets at a time. And you see the same sort of thing. The only difference is that parameter space now is much, much smaller, but you still have room for space curvature and you still have room for dark energy dynamics. And it doesn't matter what combination of data sets you look at, but you still have the systematic effect because of the Hubble constant. It moves things by half sigma. And I can just go through and show you all of these. So again, they're all consistent with the standard model, but they allow for some dark energy dynamics and they allow for some spatial curvature. But if you looked at different supernovae data, you get different constraints. They move things around by half a sigma. So if you use different GRB data analysis techniques, you get different constraints, again, half a sigma. And we saw what happened with H for the growth fact for the Hubble parameter. And I'll soon show you the most recent data, but I'm going to change gears a little bit. And we can now measure the Hubble parameter up to redshift about 2.3, either through cosmic chronometers or radial BAO. And it's more interesting to plot this so you can actually see the variation. If you just plotted H as a function of Z, it would go up really sharply and you wouldn't see the differences. So I'm plotting this. And what I've plotted here are 6 best fit models to these data. And you can see 3 of them correspond to the higher H naught and 3 of them correspond to the lower H naught. And they all show you a dip. And these are 3 sigma models that 3 sigma away from the best fit models, just illustrative. So it doesn't seem that interesting here, but we've got enough data here at low redshift to bin them. And so if I bin those data in redshift bins, and I can't do that at higher redshift because the data is way too sparse. And if I start binning them in redshift bins, that's not going to be reasonable because they correspond to huge ranges of redshift. So you can see from even from the lower data, you sort of see these are now 2 sigma error bars, and you can sort of see the change. So you get decelerated expansion and then accelerated expansion. And if you look at lambda CDM at higher redshifts, this guy's going to be less important, this guy's going to be more important, and that's why you're getting this decelerated and you're getting accelerated here because at lower redshifts, this guy is more important. And something like DESI should be able to do this out to a redshift of maybe even close to 3, and maybe with 50 to 100 bins, and they should be able to map this growth H of Z really, really well. And you can, from this data, this is from 10 years ago, you can get this transition redshift. There's probably a bunch of systematics we don't have in there. This is just a statistical error bar. So the next thing I want to do is go to the most recent data I have, and I'm just going to first focus on non-CMB data, and I'm not going to use the DESI data. So instead, what I'm going to use is BAO, HZ, and supernovae, and I'll use the Pantheon Plus, and that's where most of the statistical weight is. I'll also use quasar angular size, MG2 and C4 reverberation measured quasars, and Amati correlated GRBs that go all the way to redshift of 8.2. This goes up to redshift of 3.4, that's 1.9. And this guy is about 2.7. And I want to do this independent of CMB and independent of local calibrators. So what I'm going to do is I'm going to actually effectively measure the sound horizon and drag epoch by fitting for omega baryons and omega C and then computing that. And I'll use a bunch of models and marginalize over everything and just get the Hubble constant. Yeah.
Can I quickly ask about the error bars here? So consistently, you can see even with the Reese number on your own slides that the other groups are reporting much lower errors, often using the same Pantheon data.
So they're not using the same thing. So you're asking about this 2.4?
Yeah, the 2.4
Okay,
versus...
so we're not using any local calibrators and we're not using any CMB data. So we wanted something at lower redshifts that didn't use local calibrators and didn't use the CMB.
I see.
And yeah.
What about the time delay?
So we haven't used the time delay yet. I mean, that could be folded in also. So all of these, so we looked at a bunch of other data sets too, and I'll come back to that, but we looked at all these constraints individually and saw that the contours were consistent with each other in a statistical sense, and those are the only data sets we've used. And you could use time delay here also, but we haven't done that yet. And you can see that independent of model, it gives you roughly the same value of the Hubble constant. And if you just choose the average of this, you get 69.25. And you choose a scatter, which is plus minus 0.3 as your systematic error and add that into quadrature. That's what you get. And this is consistent with what we found with median statistics. And it's also consistent with Wendy Friedman's group with the most recent paper with the tip of the red giant branch as a local calibrator and going out in the Hubble flow with type 1a supernovae. It's a little bit lower than Adam Rees's group, somewhere about 1.5 sigma lower. And to me, the really interesting thing is these two numbers and these two error bars. And they're about 1.2 sigma apart. I mean, you can say that that's irrelevant and they're completely consistent, but this number is also consistent with the CMB. There's some future in trying to see if this error bar can be made smaller, or understanding why this error bar is the one that it's so small, and it's the only group that seems to get this really tight error, and maybe they have really, really good data, but much better than what anybody else has.
Sorry, I might have missed this, but how do you anchor your data?
So we're anchoring the data by measuring from the data omega CDM and omega baryons, and that allows you to compute in that cosmological model the sound horizon at drag. And so we don't need to use the CMB.
Okay.
I mean, the question is, I mean, how do we use the BAO data? And that's what we're doing. So we're getting that, we're measuring it individually. And that's why these error bars are so big. So some people use Big Bang nucleosynthesis to give you this, and they can get smaller errors. But so one of the reasons you believe in Big Bang nucleosynthesis is at least the deuterium abundance agrees very, very well with what's predicted in the CMB. And so you could argue by using Big Bang nucleosynthesis, you're already including some CMB data, and that's why we didn't want to include that. And potentially you can tighten this up by adding in strong lensing And there's a few other data sets which we haven't looked at so far. But so I don't know, it'd be really nice to understand why one of these error bars is a factor of 2 bigger than the other. And then if you can kind of reproduce the results with another data set that gives you ±1 and also around 73, then it's a really serious issue because it's very different from the Planck data. And that has to do with something with the cosmological model being incorrect. So the other thing that's interesting is that the Planck data, at least the PR3 data by itself favors a mildly closed model. So it depends on which data set you look at. And it's if you do P18 plus lensing, I believe it's omega curvature is minus 0.01 at maybe 1.6 sigma significance or something. I have it written down. But that goes away when you combine the CMB data with non-CMB data. But it might be that if you use dynamical dark energy, that would be different. And so it's probably worth looking at this issue in dynamical dark energy models that are non-flat and see, yeah.
So this is something I've always wondered. When you talk about geometry, does lambda CDM constrain geometry, or does geometry constrain lambda CDM?
They're independent. It depends what you mean by lambda CDM. So the standard model is usually spatially flat lambda CDM. And so the geometry is Euclidean, so 3 flat R3. But from Einstein's equations, you're allowed to have the closed geometry, the spherical 3-dimensional sphere, and the hyperboloid. And it's an observational question of what the values are for omega curvature. And it's pretty close to flat, but whether it's exactly flat is not yet clear. And so the CMB Planck by itself favors slightly non-flat geometries, closed geometries. And if you combine it with non-CMB data, it gives you flat geometry. And that's been done in the lambda CDM model where dark energy is lambda, but it's useful to look at it in the XCDM and phi CDM models. And so we're going to put back in space curvature in the XCDM parameterization. And we'll do the same thing in the phi CDM parameterization, the orange line. And then I'll just tell you the results from the same data set. And before so this is where all the constraints are coming from. And these constraints are all mutually consistent. So we looked at a lot of other data. We looked at Lusso et al. They have a correlation between X-ray and UV luminosities of quasars. And we can show quite convincingly those are not standard candles. We also looked at reverberation measured H beta AGNs. And those also have a really strange RL relation. They don't seem to work. And people have looked at starburst galaxies, these H2 starburst galaxies, and those also are not standard candles. I can talk more about this if people are interested. But using these data, we find that consistent, this is just non-CMB data, but consistent with flat geometry, deviating at most by a little more than 1 sigma. But when you look at dark energy dynamics, they typically deviate by about 2 sigma from a cosmological constant. And this has been true for a long time, that you have this 2 sigma deviation from lambda. So these guys, one example that might prove to be useful. So you have a black hole here, and you have the broadline region. And if you can measure the time delay, there's apparently a pretty good correlation between the absolute luminosity and that time delay. And so you can standardize these guys. And we're doing this with 50 to 100 AGNs now. And Rubin, at least in the deep drilling field, should get a lot more because it has probably a good enough cadence to get time delays of tens to hundreds of days. And you should get a lot more of these AGNs. And maybe if this thing holds up, that you'll have another standardizable probe. So I want to now put back in the CMB because that's got a huge amount of statistical weight. And if you put back in the CMB in these non-flat models, you can't use the scale invariant Harrison-Peebles Hughes-Ullovich spectrum because you have either closed or open geometry. So in addition to the Hubble length, you have this extra curvature length scale, and you have to come up with inflation models to get the Pos spectrum, a physically consistent Pos spectrum. So in the spatially flat case, the only reasonable thing to write down is k divided by 8 times the Hubble parameter, a Hubble constant, and that's dimensionless, and it's going to be a function of that. And people had this spectrum in 1970, way before inflation, but then inflation came along, and you could see that these spectra came from quantum fluctuations during inflation. So if you look at a closed model, you have discrete eigenvalues of the Laplacian, and you can't do the same things you can do here. And life is somewhat messy. And if you take really slow roll inflation models, both in the closed and open cases, so this is the eigenvalue of spatial Laplacian, and A is an integer, and 0 and 1 are gauge modes, and 2, 3, 4, and so on are the real physical modes. And this guy is more useful. It's Q, which is A plus 1. And that gives you a spectrum of this form, which you can analytically compute in a closed and open inflation model. But we know from the CMB, so this is because it's a very, very slow roll, it's going to give you at larger k, it's going to give you a scale invariant spectrum. And we know that that's not correct because from the Planck data, we can tell it's going to be tilted and not scale invariant. So the Planck analysis just took this really slow roll spectrum and multiplied it by k to the n minus 1. And they didn't motivate this. So we've been spending a lot of time trying to find closed inflation models that give Pos spectra close to this. And we've managed to do that, and we'll have a paper soon. But I've also computed analytically a different Pos spectrum, which I'm going to call a new Pos spectrum. And this guy I'm going to call the Planck Pos spectrum. And it's easier to just look at plots of these Pos spectra. So in the closed case and in the open case, the variations are a little more striking. So this is the scale invariant spectrum, the blue line. And this red line is the tilted, the new Pos spectrum. And this dotted line is the one that Planck used in the analysis, and they appear to have really large differences. But the error bars in the CMB data on these scales are pretty large, so you're not going to change things a lot with those differences. So now things get really, really messy. So I want to show you how to fit, what happens when you fit these models to the data. And the data we're going to use the PR3 or P18 Planck data. So it's TT, TE, EE, and low E. So that's the polarization data, as well as the lensing potential Pos spectrum. And our non-CMB data set, again, it doesn't include any DESI data. It's BAO, so there's 16, and 4 of them are growth factor of these 16. And then from velocity fields, we get another 9 growth factor, and we get 5090 Pantheon plus measurements of aberrant magnitude and 32 Hubble parameter measurements. And these data give you consistent constraints. We looked at them individually, and the constraints overlap before we did a joint analysis. And we're going to try to constrain 12 models. So 6 of them lambda CDM, 6 of them WCDM, or omega XCDM. And so 3 of these models are the flat tilted one with this spectrum, the non-flat tilted Planck spectrum, and the non-flat tilted mu spectrum. And they're going to be in pairs, and the pairs with this capital parameter, capital A sub L parameter, either fixed to unity or allowed to vary and determined from the data. And this guy is a consistency check parameter. What it does is it puts back in the 2-point lensing potential correlation function in the analysis. And you hope that at the end of the analysis, it comes back with the value unity. And that'll tell you that the best fit lambda CDM model to the Planck data predicts exactly the lensing that you see in the CMB, the C sub Ls. And it turns out when you do that, the A sub L comes back about 2.5 sigma greater than unity, telling you that the C sub L's are smoothed a little more than you'd expect in the best fit Planck model from lambda CDM. And so the results are kind of a little bit messy here. So I'll start out with A sub L equal to unity, and we find no inconsistency. So what we're doing is what's called the suspiciousness. And we can also do this with another parameterization, statistical estimator from what people have used in gravitational, weak gravitational lensing used with Higginson DIC. And so the two data sets we're going to compare are Planck 18 and non-CMB. And for the standard model, they're only 1.2 sigma inconsistent. And the same thing is Planck plus the lensing CMB plus non-CMB. And if we do this with the non-flat models, these two data sets are, in these two models, they're about 2.5 sigma inconsistent and 1.5 sigma inconsistent. So we're going to have a threshold, we're going to make some assumptions, and we're going to say things that are more than 3 sigma inconsistent are inconsistent, and those less than 3 sigma inconsistent are not inconsistent. And so these are not inconsistent. And so we can jointly analyze these data sets and measure omega curvature. And this is what we get for omega curvature. And it's very, very consistent with the flat geometry. Now, if we allow A sub L to vary and try to determine it from the data, the consistency improves compared to what it was when A sub L was fixed. And you can combine them again, and you see that they're both flat and even more consistent with flat than over here, which is half sigma away, and this is just a quarter sigma away. But A sub L is deviant from unity by about 2.5 sigma. So we have excess gravitational smoothing or excess smoothing of the C sub L's that is predicted by the best fit model. And that's not clear what's going on there. And so we don't see this in the ACT and SPT data, but their error bars are much, much bigger than the Planck error bars. So they're probably not tight enough to give you this issue. Planck, part of the group stayed together and they analyzed release of the data that's more recent than the PR3 data that they released in 2018. And that guy has less problems with this A sub L, but we haven't finished the analysis with that yet. But the more interesting thing happens when you look at ΛCDM, and there with A sub L equal to 1, these data sets, in any of these models, they're discrepant by more than 3 sigma. And what's happening here is the CMB data want to have phantom dark energy. They want omega to be less than -1. And the non-CMB data want to have quintessence dark energy. And so their contours don't overlap. And so they're inconsistent. So these models are all ruled out with A sub L equal to 1. If you allow A sub L to vary, then they're less than 3 sigma inconsistent, and you can combine them, and you can measure omega curvature, and they're also flat, but maybe a little less flat than in the lambda CDM case. But they prefer dynamical dark energy at about 1.5 sigma, and they have this issue with the weak gravitational lensing of the CMB again. And this model is important because if you look at the DESI results, so the DESI results use this equation of state as the parameterization. And you can see that at low redshift, when Z is 0, it reduces to just omega naught. And at high redshift, this becomes unity, and it becomes omega naught plus omega A. And so it's a WCDM model with a different slope at high and low redshifts. And at low redshifts, it's going to be better constrained by the non-CMB data, and high redshifts, it's going to be better constrained by the CMB data. And this model is flexible enough with this break in this slope to be consistent even at constant A sub L equal to 1. But this is just using our data compilation. And this gives us tighter constraints in the first year DESI results, where they used CMB from Planck and ACT and Pantheon Plus. They also did other supernovae, but this is what they got, and this is what we get. And you can kind of see that they're almost identical. And so what's happening here is that low redshift, you want quintessence because this is larger than -1. And at high redshift, where that's the slope, you want phantom dark energy. And this model is flexible enough to accommodate both. And if you look at this space here, or this one here, this is the non-CMB data, and that's the CMB data, and they're consistent. And once you combine them together, you can see the 2 sigma deviation from lambda CDM. So we reproduce this 2 sigma deviation from lambda CDM that DESI saw, but this is completely independent of DESI. And this 2 sigma deviation is also there when we throw away the Pantheon Plus data from our analysis. So it's not caused by the DESI data, it's not caused by the supernovae data. And I think those are 2 really important things. So if we go back and allow A sub L to vary, then we find the same sort of thing, except now the blue lines almost touch lambda CDM at 1 sigma. So the deviation from lambda CDM becomes 1 sigma, and you get back this A sub L varying from 1 at more than 2 sigma. So it's possible that in this non-physical model, that the evidence for dark energy dynamics is coming from the CMB, part of it's coming from the CMB. And we've done this, which we just put onto archive a few days ago. I haven't rewritten this slide, but we've done the flat phi CDM model with the same data compilation. And we find for A sub L equal to 1 that it deviates from the lambda CDM model at 1.3 sigma and favors quintessence dark energy. And for A sub L varying, it favors quintessence dark energy at 1.7 sigma. So all these things are 1 sigma, 2 sigma results, and they're not, I mean, I don't know what you can conclude from them, but I can start summarizing now. So I think these are the 4 main issues we have. We don't know what the dark energy is. It cannot be ruled out that some dynamics is allowed by the current data we have, and it's not very rapid dynamics. It's mild at the best. And I think BO data from DESI and then Euclid are going to be really important in the next 5 years. So the universe is probably flat, but it'd be better to understand these non-flat inflation models a little bit more. And this might be an issue more for the Planck data than it is for the standard lambda CDM model. And maybe from analysis of the PR4 data set, it'll become clearer. And we also don't know what the dark matter is. Maybe we'll get some information from these deep underground experiments or the Large Hadron Collider at CERN. And after you guys have done all of this as parts of your PhD, cosmology is not going to be over. So I'll just leave this up for a few seconds. Thank you very much.
All right, so we have time for a few questions.
Will gravity wave data at all help the analysis?
Yeah, it'll help a lot if you can find electromagnetic counterparts, black hole, neutron star, neutron star, neutron star. And I guess it's been a little disappointing that they haven't found more so far. So they might be able to measure the Hubble constant pretty accurately if they get enough of those.
You mentioned in the ΛCDM model that the sound speed being imaginary is a problem for gene instability, but that it's somehow finessed.
Yeah, so when they're doing the perturbations, they just replace the sound speed there by unity.
I mean,
because they just say it's a stiff fluid and they don't care about what's happening at the background level. And it's just
This is
much
worse
easier.
than Gene's swindle. This is like Gene's crypto scam.
Yeah, they should be using scalar field models, but you can't do those. I mean, so XCDM or WCDM, you can solve that analytically and then just plug that into your MCMC instead of running numerical integration code at each point in parameter space. That makes it much, much longer.
So I have a question. So if you back up a couple slides, not that one, those before. So of those, which are you the most optimistic to get answers for, well, you and I are right to enjoy them.
So we'll see what happens with DESI in the next 2 years or so. I don't know when they're going to release the complete data set. And maybe if they have good enough data and they've understood all their systematics, that could find dark energy dynamics. And if they can find that in a more sensible parameterization, it'll be more convincing.
Fair enough. And also, you mentioned there's someone in the middle said about not flat inflation models, which you
Yeah.
don't hear much about. So how does that work? Is it hard to is there a fine tuning problem to get to have just the right amount of curvature? Is that hard to?
So they usually do it with two epochs of inflation. So the open one is easier to explain. So what you do is you have a false vacuum, and you're sitting at the false vacuum for a while, and you can inflate and solve all your problems, and then you tunnel through that barrier. And after that, you can't have a lot of inflation. And that tunneling was computed by Coleman and DeLucia in the 70s, and they find that you nucleate an open bubble with open geometry inside of it. But there's a fine-tuning problem because if you have a lot of inflation after you nucleate that, and the curvature goes away.
Can you say a little more about that final point on dark matter, about the dwarf galaxy abundances?
So the nuclear profiles don't seem to fit the standard the CDM model. And so people have tried things like giving it some self-interaction or using scalar field dark matter to change what's happening on small scales. And I haven't followed that in great detail. I mean, this is just a qualitative statement, but maybe there's people here who know more about what's happening in clusters.
Other questions? All right, very good. Well, let's take another guess.